June 14, 2026, 1,847 meters below the surface of the Pacific Ocean. A research submarine designated DSSV-4 captured 47 seconds of footage that marine institutions have spent 8 months trying to explain away. I want to be specific about what we're dealing with here. This isn't tourist video shot through murky coastal water. This isn't sonar bounce or thermal imaging ambiguity. This is high-definition footage captured by a deep-sea research vessel equipped with military-grade low-light cameras designed for abyssal trench documentation. $4,000 per hour operating costs. A crew with a combined 70 years of deep-sea experience. Equipment calibrated to capture bioluminescent organisms at pressures that would crush a human body in under 2 seconds. What they recorded has no taxonomic classification, no evolutionary precedent, no explanation that fits inside conventional marine biology. The footage shows a humanoid figure, not humanoid in the way a seal looks vaguely mammalian if you squint. Humanoid in bone structure, in facial proportions, in the way it moves its head to track the camera with what appears to be deliberate focus. It has a face, not a rostrum, not a snout. A face with forward-facing eyes, a defined nose bridge, a jaw that suggests articulation capability beyond simple feeding mechanics. The skull structure reads mammalian, primate even. But where the torso should transition to legs, there's a continuation into something else entirely. A posterior extending into what can only be described as a caudal fin, not vestigial, not decorative. A fully functional propulsion system covered in scales that catch the submarine's lights and throw them back in patterns that shouldn't exist in nature. And it has gills, visible, functioning respiratory slits along what would be the rib cage in a human body. They pulse. You can see them cycle in the footage, open, close, filter. While it stares at the camera with eyes that reflect light like a primate's, it breathes like a fish. The video has been analyzed by 3 separate marine biology departments. None of them have published their findings. 2 of the research teams have since dissolved. The third stopped returning calls in November. The DSSV-4 expedition was scheduled to run for 6 weeks. It was terminated on June 17, 2026, 3 days after this footage was recorded. The stated reason was equipment malfunction. The crew was debriefed and released. None of them have given public interviews. None of them have appeared at marine research conferences. 2 took positions at landlocked universities. 1 left academia entirely. The footage you're about to see was not officially released. It was leaked. The metadata shows it was copied from the submarine's onboard storage on June 16th, 1 day before the expedition was shut down. Whoever pulled it knew they had limited time. What you're looking at is either the most significant cryptozoological evidence ever captured or documentation of a species that certain institutions have decided the public isn't ready to know about. By the end of this analysis, you'll understand why both possibilities are terrifying. This is the June 2026 footage, frame by frame. With every detail that's been systematically ignored by the organizations that should be shouting about this from every oceanographic institution on the planet. The DSSV-4 was operating in the Clarion-Clipperton Zone, a deep-sea region spanning approximately 1.7 million square miles between Hawaii and Mexico. The target depth was the Valdivia Trench, a fracture zone that drops to just over 2,000 meters, deep enough to be in permanent darkness, but shallow enough for the research-grade cameras to function without the light-scattering issues that plague footage from the true abyssal depths. The mission parameters were standard: document mineral nodule formations and catalog extremophile bacterial colonies. The kind of work that gets funding because it has industrial applications, mapping potential deep-sea mining sites. The crew consisted of Dr. Sarah Chen, a geomicrobiologist with 12 years of submarine research experience, Marcus Holt, the pilot, former Navy with over 300 deep dive hours logged, and Dr. Raj Venkatesh, a marine geologist specializing in tectonic activity. All three had published extensively. All three had reputations for precision documentation. The timestamp on the footage reads 09:47:22 UTC. Morning surface time. Down in the trench, time doesn't mean anything. It's been dark for 200 million years. The submarine's external camera array includes 6 synchronized units: forward, aft, port, starboard, dorsal, ventral. The footage comes from the forward primary, a Sony UMC-S3CA modified for pressure housing and low light sensitivity. It shoots in 4K at 60 frames per second. The housing is rated to 3,000 meters. At 1,847 meters, it was operating well within tolerance. The lighting is provided by LED arrays that can be dimmed or brightened depending on what the camera is trying to capture. For this segment, they're set to about 60%, bright enough to illuminate the water column roughly 20 meters ahead, but not so bright that particulate matter creates a blinding scatter effect. You can see the beam cutting through the water. You can see the faint drift of marine snow, organic debris constantly falling from the photic zone above. And then, at 9:47:29 UTC, something enters the frame from the upper left. It's not a fish. The movement is wrong. Fish at that depth move in specific ways: slow, energy-conserving, often hovering in place. This moves with intention. It doesn't drift into the light. It swims into it, deliberately. The tail, and I'm going to call it a tail because there's no other term that fits, moves in a vertical oscillation pattern, up and down, like a whale, like a dolphin, not side to side like a fish. That's a mammalian propulsion system. That's how creatures with horizontal tail flukes generate thrust. Except it's not a whale, it's not a dolphin. The figure enters full frame at 9:47:31. For the next 8 seconds, it holds position roughly 12 meters from the camera. The submarine is in slow forward drift, about a quarter knot. The creature is matching speed, not passively being pushed by current, actively maintaining distance. The camera's autofocus locks on. The image sharpens. The face is the first thing that stops you. The proportions are wrong for any known marine species. The eyes are forward-facing, set in a skull that has orbital sockets, brow structure, cheekbone definition. The distance between the eyes is roughly consistent with human facial architecture. There's a nose, not a blowhole, not a nostril slit. A protruding structure with what appears to be cartilage definition. The mouth is closed, but you can see the line of it. It's horizontal. It suggests lips, not a beak or a fixed jaw structure. The skin texture is difficult to categorize. It's not smooth like a dolphin. It's not scaled like a fish in the traditional sense. Under the LED lights, it has an almost opalescent quality, like there's a chromatophore layer underneath, the kind of adaptive camouflage cells you see in cephalopods. But the base tone reads as pale, almost translucent. You can see vascular structures underneath in certain frames, branching patterns that suggest a circulatory system close to the skin surface. The torso is lean, narrow shoulders, defined musculature visible along what would be the clavicle and deltoid regions in a human. Arms, and yes, they're arms, extend from the shoulder joints. They're longer proportionally than human arms. The hands are visible for 3 frames when the creature adjusts its position. 4 fingers, possibly 5. It's difficult to count because they're partially webbed. The webbing extends from what looks like the base knuckle to about midway down each digit. The fingers themselves are elongated. They taper. There might be claws. There might just be hardened keratin tips. The ribcage area shows the gills. There are 3 visible slits on what would be the right side of the torso, angled posteriorly. They're not flush with the skin. They have structure, raised edges, almost like the creature can flare them open or compress them shut. In the footage, they're cycling. You can watch them pull open, hold, then press closed in a rhythm, roughly 1 cycle every 4 seconds. That's a respiration rate. That's breathing. Below the rib cage, the anatomy transitions. The waist tapers, but instead of hips and legs, there's a continuous posterior extension. It's muscular. You can see the movement ripple through it with each tail stroke. The scales, or whatever the surface structure is, start becoming visible around what would be the lower lumbar region in a human. They're not the overlapping plate scales of a fish. They're smaller, more densely packed, almost tile-like, and they're refracting the light. That's the part that doesn't make sense optically. Bioluminescence in deep-sea organisms usually presents as localized photophores, specific light-producing cells. This is different. The entire tail surface seems to be catching the submarine's LED light and throwing it back, but not uniformly. It pulses. Sections brighten and dim in what looks like a pattern. It's too regular to be random light scatter, too coordinated. At 9:47:39, the creature rotates slightly. The tail moves in a full stroke, dorsal to ventral, and the figure shifts position about 2 meters to the right. The movement is fluid. There's no struggling against water resistance. It's controlled, efficient. The kind of motor control that suggests a proprioceptive system and muscular coordination on par with apex marine predators. And then it looks directly at the camera, not in the general direction, not tracking movement. It rotates its head, tilts it slightly downward, and the eyes focus on the lens. You can see the pupils contract. That's a response to light. That's an iris adjusting. For 2 full seconds, it holds that gaze. In frame 1455, you can see the reflection of the submarine's lights in its eyes. The tapetum lucidum, the reflective layer that nocturnal and deep-sea animals have, is throwing back a greenish-gold eye shine. The same thing you see in cats, in owls, in animals that hunt in low light. But the structure of the eye itself, the shape of the reflection, suggests a forward-focused predator's gaze. Binocular vision, depth perception, it blinks once. A horizontal membrane closes from the side and retracts, nictitating membrane. Then the outer lid closes vertically and reopens, 2 separate eyelid systems. That's an adaptation you see in marine reptiles and some diving birds, protection for the eye in different environmental conditions. At 9:47:43, the creature's mouth opens slightly, not wide, just enough to see that there's an internal structure. The lighting isn't good enough to make out dentition, but there's a tongue, or something analogous to a tongue, movement inside the oral cavity, and for just a moment the gills flare wider. All 3 slits pull open simultaneously, then compress shut hard. It's the same kind of aggressive respiration spike you see in sharks when they're agitated, a rapid oxygen intake. Then it moves. Not slowly, not with the languid drifting pace it had before. The tail snaps through a full power stroke, and the figure accelerates backward and to the left. In under 2 seconds, it's at the edge of the light cone. 1 more stroke, and it's gone, completely outside the range of the LEDs. The water swallows it. The footage continues for another 31 seconds. The camera stays fixed forward. The submarine continues its slow drift. There's nothing but marine snow and empty water. At 9:48:16, the recording cuts. Not a stop command, a cut. The metadata shows the file was manually trimmed. Whoever leaked this edited it down to just the encounter. Everything before and after was removed. 47 seconds of footage, 29 seconds where the creature is fully visible, and in those 29 seconds, every single frame contradicts what we think we know about evolutionary biology, deep-sea physiology, and the possibility of large, unidentified vertebrates existing in surveilled ocean zones. The resolution is high enough that independent analysts have been able to extract anatomical measurements. Assuming the creature was 12 meters from the camera, which matches the submarine's forward depth sensor reading, photogrammetry analysis suggests a total length of approximately 1.8 to 2 meters. The head accounts for roughly 13% of that length. The torso and tail are nearly equal proportions. The arm span when extrapolated from the visible shoulder width, would be close to 1.5 meters. That's not a giant. That's roughly human-sized. That's something that could theoretically exist in population numbers significant enough to maintain genetic viability without being constantly photographed. It's small enough to be elusive, large enough to be apex in its environment. 3 marine biology labs were given the footage in July 2026. All 3 were told it was captured during the DSSV-4 expedition. All 3 were asked for preliminary identification. The first lab, based out of Scripps Institution of Oceanography, responded with a request for metadata verification. They wanted to confirm the depth reading, the timestamp, the camera specs. When provided with that data, they went silent. No report was ever published. 2 of the researchers listed on the initial inquiry left Scripps by September. One took a position at a university in Colorado, landlocked, no marine access. The second lab, a private marine research contractor that works with NOAA, returned a 2-page assessment. The summary concluded, unknown species, anatomical features inconsistent with known vertebrate clades, recommend comprehensive taxonomic review and immediate follow-up expedition. The recommendation was ignored. The contract with NOAA was not renewed. The lab dissolved in October 2026. The third lab never issued a formal report. An internal email later leaked included the line, "If this is real, we're not equipped to classify it. If it's fabricated, it's the most sophisticated hoax in marine biology history. Either way, we can't publish." No one published. No one went on record. And 3 days after the footage was captured, the DSSV-4 surfaced ahead of schedule. The mission was scrubbed, and the crew disappeared into non-disclosure agreements and career relocations. The footage exists. It's been analyzed by forensic video experts who found no evidence of digital manipulation. The compression artifacts are consistent with the camera model. The lighting physics match the LED array specs. The water particulate drift follows fluid dynamics for the stated depth and current conditions. If it's a hoax, it was made with access to military-grade equipment, detailed knowledge of deep-sea environmental conditions, and a level of anatomical knowledge that suggests input from marine biologists and evolutionary anatomists. Or it's exactly what it looks like, and no one knows what to do with that. Dr. Elena Vasquez has spent 19 years studying marine vertebrate evolution. She has a PhD in comparative anatomy from UC Berkeley and a secondary specialization in adaptive morphology. She's published 43 peer-reviewed papers on everything from whale skeletal adaptation to the evolution of fish fin structures. When I sent her the footage in January 2027, she watched it 4 times before responding. What she told me was this: "I can't tell you what it is. I can tell you what it isn't, and that's almost everything." The problem starts with the head. Forward-facing eyes indicate predation and depth perception, binocular vision that allows distance calculation. In marine environments, that trait shows up in exactly 3 contexts: apex predators like sharks that need to judge striking distance, ambush hunters like octopi that need spatial precision, and intelligent species like dolphins that use it for social coordination and tool manipulation. But the eye placement on this creature reads closer to primate than marine predator. The orbital sockets are too deep. The spacing is too narrow. That's a terrestrial configuration. That's the face of something that evolved to navigate 3-dimensional space above water, not in it, except it has gills. Functional respiratory slits that are cycling in the footage with the rhythm of an organism extracting dissolved oxygen from water. That's not vestigial anatomy. That's not evolutionary remnant. Those gills are working. Dr. Vasquez walked me through what that means. Gills are an ancient adaptation. They show up early in vertebrate evolution, and they work beautifully for organisms that never need to leave water. But the trade-off is significant. You can't support a large body mass with gill respiration alone once you start developing complex terrestrial features like a robust skeletal frame or a high metabolism brain. That's why marine mammals went the other direction. They evolved lungs, came back to the ocean, and kept the lungs. It's more efficient for a warm-blooded, large-bodied animal. Gills would limit you. But this creature has both systems, or at least the anatomy suggests it might. The torso structure, the ribcage definition, the way the chest cavity appears to have volume, that suggests lungs, or at minimum a respiratory system more complex than simple water filtration. And yet, the gills are there, visible, functioning. That's not a compromise, Vasquez said. That's two separate evolutionary solutions occupying the same organism. That shouldn't be stable. That shouldn't work. Then there's the tail. The propulsion system visible in the footage uses vertical oscillation. The tail moves up and down, not side to side. That's how cetaceans swim. Whales, dolphins, porpoises, they all evolved from terrestrial mammals that returned to the ocean, and they kept the mammalian spinal flexibility that allows vertical tail movement. Fish move their tails laterally because their spinal columns are built for that kind of articulation. The musculature, the vertebral structure, the tendon attachments, all of it supports side-to-side motion. This creature's tail moves like a mammal's, but it's covered in scales, and it ends in a structure that looks more like a caudal fin than the horizontal flukes you see on a whale. The fin edges are defined. There's no cartilage droop. It holds its shape even when not actively stroking. That's a fishtail architecture combined with mammalian kinetics. Dr. Vasquez paused the footage at frame 1702, where the creature is mid-stroke and the entire tail structure is visible in profile. "Look at the flexibility gradient," she said. "Near the body, there's a lot of articulation. You can see the musculature compress and extend. But further down toward the tail tip, it's stiffer. That's exactly backward from how whale tails work. Whales have rigid peduncles near the body and flexible flukes at the end. This has flexibility at the base and rigidity at the terminus. That's a design for fast, precise maneuvering, not endurance swimming. That's a predator's tail." I asked her what kind of predator. "One that shouldn't exist," she said. "The arm structure presents another problem. The shoulders are too mobile. In the footage, when the creature adjusts its position at 9:47:39, you can see the range of motion. The arm rotates in what looks like a full ball and socket articulation. That's primate-level shoulder mobility. Marine mammals have restricted forelimb movement because their arms evolved into flippers, rigid, paddle-like structures optimized for steering, not manipulation. This creature has arms that could reach, grasp, manipulate objects. The hands are webbed, yes, but the fingers are distinct. They have joints. They have individual articulation." "That's tool-use morphology," Vasquez said. "That's the anatomy of something that interacts with its environment in complex ways. You don't get hands like that unless there's evolutionary pressure for fine motor control." And then there's the face again, because it's not just the eyes, it's the nose, the jaw, the proportions that suggest a skull capable of housing a brain with significant frontal lobe development. Dr. Vasquez pulled up a comparative image, a human skull next to a dolphin skull next to a great white shark skull. "Look at the brain case volume relative to body size," she said. "Dolphins have large brains for their mass because they're intelligent, social, and they navigate complex acoustic environments. Sharks have small brains relative to their size because they're efficient predators that rely on sensory systems, not cognition. Humans have disproportionately massive brains because we're behaviorally complex and our survival strategy is cognitive, not physical." She overlaid a rough skull projection based on the creature's visible head structure in the footage. The cranial volume estimate came back closer to human than dolphin. Adjusted for body size, the brain-to-body ratio suggested something in the range of great apes. If that projection is even remotely accurate, Vasquez said, you're looking at an organism with cognitive capacity, not fish-level stimulus response, not even dolphin-level problem-solving, potentially primate-level abstraction. That's when she stopped calling it a creature. She started calling it an individual. I asked her what evolutionary path could possibly produce this combination of features. She was quiet for almost a minute. Then, there isn't one, not in any model we have. You'd need a vertebrate lineage that split off before the fish tetrapod divide, maintained aquatic respiration, but somehow independently evolved mammalian characteristics, warm-blooded metabolism, complex cognition, manipulative limbs, in parallel with terrestrial evolution. That's not just unlikely. That's functionally impossible given what we know about evolutionary timelines and environmental pressures. Or, she offered, it's an extreme case of convergent evolution, where unrelated lineages develop similar features because they're solving the same environmental problems. Except convergent evolution usually produces analogous structures, not identical ones. Bird wings and bat wings both allow flight, but they're built differently. This creature's eyes don't just serve the same function as primate eyes, they have the same architecture. The third option, Vasquez said, is that it's not from our evolutionary tree at all. I asked what she meant. I mean, maybe it didn't evolve here. Maybe it's a relic population from a lineage we thought went extinct. Maybe it's been isolated so long in an environment so specific that it followed a developmental path we have no reference for. Or maybe she stopped. Maybe we're not as alone on this planet as we think we are. Dr. Hao Chen, a biomechanics researcher at MIT, focused on the movement patterns. I sent him just the section of footage where the creature is in motion, the approach, the hover, the rapid retreat. He sent back a 12-page analysis. The swimming efficiency was what caught his attention first. The stroke rate is low, he wrote, approximately one full tail oscillation every 1.2 seconds during the hovering phase. That's slow for something maintaining position against current. It suggests either enormous muscular power per stroke or hydrodynamic efficiency we don't see in known marine animals. He calculated the thrust required to hold position at that depth, factoring in the water density and the estimated current speed based on marine snowdrift in the background. The creature would need to generate roughly 80 newtons of force per stroke to stay in place. For a body that size, that's high output. That implies fast twitch muscle fiber density comparable to a marlin or a tuna, fish that are built for explosive speed. But the creature isn't holding rigid like a tuna, it's making constant micro-adjustments. The tail makes small corrective flicks between the major strokes. The torso rotates slightly. The arms shift position. That's active stabilization, Chen wrote. That's neurological control and proprioceptive feedback. You see that in organisms with complex motor systems and high cognitive load dedicated to movement planning. Then it accelerates. The retreat sequence at 9:47:43 happens over 1.7 seconds. Chen estimated the creature covers approximately 15 meters in that time. That's an average speed of just under 9 meters per second. For comparison, a bottlenose dolphin's burst speed tops out around 8 meters per second. A yellowfin tuna can hit 20, but only in short bursts, and only because their entire body is optimized for speed. This creature accelerates from hovering to near dolphin speed in under 2 seconds, then vanishes beyond the light range. That's not casual movement, Chen noted. That's escape behavior. That's a startle response. Something triggered a rapid exit, and it had the musculature and neurological wiring to execute it immediately. I asked him if the anatomy in the footage could support that kind of performance. If the muscle tissue has the fiber density and the metabolic support, yes. But that requires a cardiovascular system capable of delivering oxygen and flushing lactate fast enough to prevent fatigue. That requires a heart. That requires blood. That requires, most likely, a closed circulatory system with significant pressure capacity. He paused the footage on the frame where the gills are flared. If those gills are the primary respiration system, they'd need to be extraordinarily efficient to support that activity level, more efficient than any fish gill system we've documented. Or, he didn't finish the sentence in the report. When I called him, he said it out loud. Or it has lungs too, and it was holding its breath. The eyes are what keep you awake, not the anatomy, not the tail mechanics or the gill structure, the eyes. Because at 9:47:41 UTC, for exactly 2 seconds, that creature makes a decision. You can see it happen. Dr. Amira Okafor is a comparative cognition researcher at Duke University. She studies decision-making behavior in non-human species, dolphins, ravens, octopi, great apes, animals we've confirmed possess what we carefully call complex cognitive processing, because we're still uncomfortable with the word intelligence when it's not attached to humans. I sent her the footage with no context, just the clip. I asked her what she saw. She called me 6 hours later. That's assessment behavior, she said. That's not reflexive tracking. That's not prey-stimulus response. That thing is evaluating the submarine. Walk through it frame by frame. The creature enters the light cone at 9:47:29. It doesn't startle. It doesn't flee. It adjusts its position and holds. For 8 seconds, it maintains a fixed distance while the submarine continues forward drift. That's not passive observation. That's active station keeping while gathering information. The head movement is deliberate. At 9:47:33, it tilts approximately 15 degrees downward. The eyes track the camera housing, not the lights, the camera. There's a visible shift in focal point. The pupils contract slightly, then stabilize. That's accommodation. That's the eye adjusting focus to examine a specific object at a specific distance. Predators track movement, Okafor explained. Prey track threat. But tool users and problem solvers track objects. They examine structure. They assess function. What you're seeing in that footage is object-oriented attention. It's looking at the camera the way a chimpanzee looks at a puzzle box, the way a dolphin examines a novel tool. It's trying to understand what it is. At 9:47:39, the creature rotates slightly to the right and shifts position. The movement brings it 2 meters closer to parallel with the submarine's trajectory. The angle changes. It's no longer head-on. It's viewing the submarine from a different perspective. That's strategic repositioning. That's gathering additional visual information from multiple angles. Okafor pulled up comparison footage, clips of dolphins investigating underwater cameras, octopi approaching submersibles, sea lions examining diving equipment. In every case, there's a pattern: initial approach, cautious assessment, experimental interaction. The animal tests boundaries. It touches, it probes, it retreats, and approaches again. That's curiosity behavior, combined with risk assessment. This creature doesn't touch. It observes. It holds distance. The closest it comes is 12 meters, and it never crosses that threshold. That's threat radius management, Okafor said. It's identified a safe distance, and it's maintaining it deliberately. That's not instinct. That's calculated caution. Then the eyes lock on. Frame 1455 through frame 1537. 2 full seconds of direct, sustained eye contact with the camera lens. Okafor went quiet when she saw it. Then, that's recognition. Not recognition as in familiarity. Recognition as in category identification. The creature has parsed the visual information, the lights, the metal housing, the mechanical structure, and it's understood that it's looking at technology, at something constructed, at evidence of intelligence that isn't its own. Watch the pupils, she said. The dilation cycle is visible across the frames. Contract, hold, dilate slightly, contract again. That's processing. That's cognitive load. The brain is working. When you see that pattern in primates, it correlates with problem-solving activity. The visual cortex is feeding information to higher processing centers. The organism is thinking, and then it blinks. The nictitating membrane slides horizontally across the eye first, a protective reflex common in aquatic species, but then the main eyelid closes vertically and reopens. That's a voluntary blink. That's not moisture maintenance. That's a reset. The kind of blink you make when you're surprised, when you're considering something unexpected, when your brain needs a fraction of a second to recalibrate. At 9:47:42, the mouth opens, just slightly. The gills flare hard. All three slits pull wide, then compress. Okafor noted the timing. That's a physiological stress response. Increased oxygen intake right before a high-energy action. It's preparing to move. But there's a half-second delay. The gills flare at 09:47:42.8. The tail doesn't stroke until 09:47:43.1, 0.3 seconds. That's not reflex. Reflex is instantaneous. Stimulus triggers action without conscious mediation. This has a gap, a decision window. Something made it decide to leave, Okafor said. And whatever that was, it wasn't the submarine's presence. It had been observing the submarine for 14 seconds. It didn't flee on contact. It fled after assessment. I asked what could trigger that. Understanding, she said. It figured out what it was looking at. And it decided the risk had changed. The retreat itself is controlled, not panic flight. The creature doesn't thrash or dart erratically. It executes a clean acceleration vector, backward and left, out of the light cone, along a path that maximizes distance while maintaining visual orientation toward the submarine until it's beyond camera range. That's an escape route. That's planned egress. Show that movement pattern to any animal behaviorist and they'll tell you the same thing, Okafor said. That's intelligent evasion. That's not running from a threat. That's withdrawing after reconnaissance. Dr. Okafor has spent 2 decades studying how non-human animals solve problems, make decisions, demonstrate what we clinically call executive function. She's cautious with language. She doesn't anthropomorphize. She doesn't project human cognition onto other species. But when I asked her directly what she thought was happening in those 47 seconds, she didn't hedge. That's a sentient encounter, she said. 2 intelligent species observing each other. One had a submarine and a camera. The other had 14 seconds to decide what that meant. And then it left. Not because it was afraid, because it chose to. There's a concept in comparative cognition called theory of mind, the ability to attribute mental states to others, to understand that other beings have thoughts, intentions, knowledge separate from your own. It's considered a hallmark of higher intelligence. Humans have it. Great apes demonstrate it in experimental settings. Dolphins show evidence of it. Ravens might possess a version of it. The test is usually some variation of this. Does the animal understand that you don't know what it knows? Can it model your perspective as distinct from its own? Okafor walked me through the markers. If an organism has theory of mind, it doesn't just react to your behavior. It anticipates your behavior based on what it thinks you know. It deceives. It communicates selectively. It tailors its actions based on its model of your awareness. In the footage, the creature approaches a novel object, a submarine it has likely never encountered before, operating in a trench region that sees maybe 1 manned research dive per year. It doesn't know what the submarine is, but it observes. It repositions for better visual angles. It focuses on the camera, the specific component that's pointed at it, suggesting it understands directional observation. And then it leaves. Not when the submarine moves toward it. The sub is in slow drift the entire time. Not when the lights brighten. The LED array stays constant. It leaves after prolonged eye contact. After the moment when, if it has theory of mind, it would have understood. That thing is watching me. It knows I'm here. That's the decision point, Okafor said. If it has even basic theory of mind, that's when it recognizes mutual observation. That's when it understands it's been seen, and it decides that's unacceptable. There's one more detail. It happens fast. Frame 1690 through frame 1702, right before the retreat. The creature's right arm moves, not adrift, not a passive float. The shoulder rotates, the elbow joint flexes, and the hand shifts position. The fingers extend slightly, then contract. It's a small movement, subtle, but it's deliberate. Okafor froze the sequence. That's a gestural interrupt. That's motor planning for potential interaction, then abort. It started to reach, then stopped itself. Reach for what? The submarine is 12 meters away, far beyond physical contact range. Doesn't matter, she said. The impulse was there. The neural pathway fired. Extend toward object. Then higher processing overrode it. No, withdraw. That's executive control. That's inhibition of prepotent response. That's one of the clearest signatures of volitional behavior. I asked if animals do that. Yes. When they're thinking, when they're uncertain, when they're weighing options. She looked at the frozen frame, the creature suspended in water, arm half extended, eyes locked on the lens. That's not a fish responding to stimuli. That's a person deciding what to do next. She caught herself. Not a person, but something person-adjacent, something with enough cognitive architecture to model scenarios, inhibit impulses, and execute planned behavior. The footage ends with 31 seconds of empty water. The creature is gone. It didn't circle back. It didn't linger at the edge of visibility. It made one rapid exit and disappeared entirely. Okafor noted that too. If it was just startled, you'd expect secondary behavior. Curiosity return, territorial display, continued monitoring from a distance. This is single action withdrawal with no follow-up. That's threat avoidance protocol. That's an organism that has assessed danger and committed to full disengagement, which means it understood the submarine as potential danger. Not immediate. It didn't flee on first sight, but eventual, possible. Something to be avoided now that it's been identified. That's predictive modeling, Okafor said. That's, I don't know what this is, but things that watch me might be things that hunt me. I'm leaving. Before we ended the call, I asked Dr. Okafor the question I'd been holding since I first watched the footage. If this creature has the cognitive capacity the behavior suggests, what does that mean? She was silent. Then, it means we're not the only ones down there who know they're being observed. It means the ocean might contain intelligence we've been looking past, because we didn't think it could look like that. And it means whoever operated that submarine just made first contact, and the other side said, no thank you. March 8, 1943, 03:20 hours local time. USS Grouper, a Gato-class submarine operating in the Western Pacific, recorded an entry in its official deck log that was classified until 2007. The submarine was running at periscope depth approximately 90 nautical miles southeast of the Marshall Islands when sonar detected what the operator described as biological contact exhibiting non-standard acoustic profile. Lieutenant Commander Howard Gilmore ordered the boat to silent running and brought her to full stop at 70 meters. The sonar contact held position roughly 40 meters off the starboard bow. No engine noise, no cavitation signature, just movement. The sonar operator, Petty Officer 2nd Class Robert Chen, logged the contact as exhibiting controlled vertical displacement inconsistent with known marine fauna. Chen is dead. Died in 1987. But his grandson, Dr. Michael Chen, a naval historian at the University of Washington, inherited his papers. Among them was a personal journal that Robert Chen kept during his Pacific deployment. The entry for March 8, 1943, goes further than the official log. The sound signature was wrong. I've tracked whales, tracked dolphin pods, tracked every kind of fish that makes noise down there. This was something else. It moved too deliberately. It held depth like it was waiting. When the captain ordered us to drift forward, it withdrew, matched our movement exactly, staying at the same distance, like it was maintaining position relative to us on purpose. After 6 minutes, it descended rapidly and we lost contact. The captain ordered the log entry sanitized. He told me directly, "We heard a whale." That's what the report would say. But in the wardroom afterward, he said something I never forgot. He said, "We're not the only ones hunting in these waters, and I don't think what we tracked was hunting fish." The grouper's official log lists the incident as probable cetacean contact, no threat assessment required. It was one line in a document that spans 300 pages covering 8 months of patrol. It should have disappeared into the archives. But Dr. Michael Chen found it because he was researching his grandfather's service record. And when he read the journal entry, he cross-referenced the coordinates. The grouper's position on March 8, 1943, 7 degrees 41 minutes north, 167 degrees 52 minutes east. Depth at that location, approximately 1,950 meters. The seabed topography is listed in modern naval charts as part of an unnamed fracture zone in the western Pacific Basin. It's not a major trench. It doesn't have the name recognition of Mariana or Tonga. But it shares geology with the Clarion-Clipperton region, volcanic substrate, hydrothermal activity, deep rifts that drop off rapidly from relatively shallow shelving zones. The DSSV-4's position on June 14, 2026, 13 degrees 51 minutes north, 131 degrees 24 minutes west. Different hemisphere, different ocean. But the depth profile is nearly identical, 1,847 meters. The geological features match. Volcanic fracture zone, minimal human traffic. One research dive every 2 to 3 years, if that. Dr. Chen didn't make the connection until I sent him the DSSV-4 footage in February 2027. He watched it once, then called me. "The movement pattern," he said. "The way it holds position and then withdraws when the submarine advances. That's what my grandfather described. Exactly that." I asked if he thought the 1943 contact was the same species. I think the 1943 contact was in the same location doing the same thing for the same reason. My grandfather's journal says the sonar profile indicated something large, highly maneuverable, and exhibiting deliberate positional control. He wrote that it felt like being watched. Those were his words. He was a sonar operator. He spent 2 years listening to the ocean, and he said this was different. The grouper wasn't the only World War II submarine to log anomalous biological contacts. Between 1942 and 1945, at least 9 U.S. Navy submarines operating in the Pacific Theater filed reports describing sonar contacts that didn't correlate with known marine life. Most were dismissed as equipment malfunction or misidentified whale signatures, but 3 of them share specific details: controlled depth maintenance, positional mirroring of the submarine's movement, and rapid vertical displacement upon approach. USS Harder, January 1944, near the Palau Islands. Depth, 1,820 meters. Contact described as large biological, non-aggressive, withdrew upon active sonar ping. USS Tang, July 1944, Philippine Sea. Depth, 2,100 meters. Contact maintained parallel course with the submarine for 11 minutes before descending beyond sonar range. USS Batfish, March 1945, East China Sea. Depth, 1,780 meters. Sonar operator noted acoustic return suggesting structured movement inconsistent with passive drift. All 3 submarines were operating in deep Pacific fracture zones. All 3 contacts occurred in low-traffic regions far from commercial shipping lanes, and all 3 logs were classified under biological contact, no actionable intelligence, and filed away. Dr. Chen pulled every declassified patrol report he could access. The Navy didn't care about fish, he said. They cared about enemy subs, surface contacts, potential threats. Anything biological got a single line in the log, and that was it. But if you read between the lines, if you look at the language the sonar operators used, there's a pattern. They knew they were tracking something that wasn't behaving like normal marine life. They just had no framework to report it as anything else. In 1977, the French bathyscaphe Archimede was conducting geological surveys in the Clarion-Clipperton Zone as part of a mineral exploration contract. The mission was commercial, not military, so the data wasn't classified. The survey logs are publicly available through the French Oceanographic Archives. On August 12, 1977, at a depth of 1,950 meters, the Archimede's external camera array captured approximately 30 seconds of footage showing what the operator described as unidentified megafauna, possibly undocumented cephalopod species. The footage quality is poor. The cameras were designed for geological work, not biological observation. The lighting is harsh and creates significant backscatter. But in frame-by-frame analysis, you can see something moving through the water column roughly 20 meters from the bathyscaphe. It's large. The size estimate in the log suggests 3 to 4 meters in length. The movement is smooth, not the pulsing jet propulsion of a squid. And for 6 frames, there's a visible profile that doesn't match any known deep-sea organism. The French team logged it as probable giant squid, insufficient image quality for taxonomic classification. No follow-up investigation was conducted. The footage sat in the archives for 50 years until a marine biology graduate student digitized the survey records as part of a research project on deep-sea biodiversity documentation. She flagged the August 12th entry because the size estimate seemed inconsistent with known cephalopod species in that region. I contacted her. She sent me the digitized frames. In frame 18, when the object rotates slightly, you can see structure, not tentacles, not the fluid, boneless movement of a cephalopod. There's rigidity, segmentation, something that could be a spine, something that could be limbs. The resolution isn't good enough to confirm, but the movement profile, the way it holds depth, adjusts position, then accelerates vertically and disappears, matches the DSSV-4 footage, matches the 1943 sonar contact, matches every one of the World War II submarine logs that described controlled, deliberate biological movement in deep fracture zones. 83 years, 3 separate incidents documented across different decades, different research missions, different ocean basins, all in the same depth range, all in geologically similar environments, all describing the same behavior, observation, positional control, withdrawal. Dr. Chen laid it out. If these are the same species or related species, that's not a single anomaly, that's a population. That's organisms occupying a consistent ecological niche across a wide geographic range. That's established territory, which means the June 2026 footage didn't capture a lone aberration. It captured something that's been there all along. In the trenches, in the fracture zones where the ocean floor drops away and the light never reaches. Regions we've mapped geologically but barely explored biologically. The Mid-Atlantic Ridge has fracture zones that match the depth and geology. The Indian Ocean has rifts we've surveyed exactly twice. The Southern Ocean around Antarctica has abyssal trenches that have never seen a manned submersible. Thousands of kilometers of deep ocean where the conditions are right. The human traffic is nearly zero, and something could live undetected for as long as it stayed below 2,000 meters. I asked Dr. Chen if he thought the Navy knew. He was careful. I think the Navy logged contacts they couldn't explain and didn't prioritize. During wartime, if it's not hostile, it's irrelevant. During peacetime, if it's biological, oceanography handles it. But oceanography doesn't have submarines. They have research vessels that rarely go below 1,000 meters. So the data sits in military archives, and the researchers never see it. Until now. until footage clear enough to be undeniable ends up in the hands of people willing to ask why no one's talking about it. The coordinates from 1943 and the coordinates from 2026 are separated by 83 years and 11,000 kilometers. But the depth is the same, the geology is the same, and the behavior is the same. That's not coincidence. That's habitat. That's a species that knows where it belongs and has stayed there long enough to be encountered across human generations. The DSSV-4 didn't discover mermaids. It rediscovered them. The footage has audio. Most people don't realize that because the visual is overwhelming enough that you don't think to listen. But the DSSV-4's camera array includes integrated hydrophones, underwater microphones designed to capture ambient ocean sound for environmental monitoring, standard equipment on research submarines, the audio recorded simultaneously with the video. For the first 23 seconds, it's exactly what you'd expect. Low-frequency rumble from the submarine's maneuvering thrusters, the faint metallic creak of the pressure hull adjusting to depth changes, the white noise hiss of water movement across the hydrophone membranes, nothing unusual. At 09:47:38 UTC, something changes. Dr. Sarah Kendrick is an acoustic ecologist at Cornell's Bioacoustics Research Program. She's spent 15 years studying marine mammal communication, whale song structure, dolphin signature whistles, the click patterns of deep-diving beaked whales. I sent her the audio file isolated from the video, no context, just the waveform. I asked her what she heard. She called back in 4 hours. "There's a signal," she said, "buried under the mechanical noise. It's faint, but it's there, and it's not random." She sent me a spectrogram, a visual representation of sound frequencies over time. For the first 23 seconds, it shows exactly what the human ear hears: broad spectrum noise from the submarine, low-frequency ambient ocean rumble. Then at 09:47:38, a new element appears, a series of pulses in the 1.2 to 1.8 kilohertz range. They're organized, regular intervals. Each pulse lasts approximately 0.3 seconds with 0.4 second gaps between them. That's not mechanical, Kendrick said. Mechanical noise is either constant or random. This has structure, this has patterning. The pulses continue until 9:47:43, exactly 5 seconds. 12 distinct pulses total. Then they stop. The audio returns to baseline submarine noise and empty ocean sound. The timing is what made Kendrick pull the video. The pulses begin at 9:47:38. That's 9 seconds after the creature enters the frame. That's 3 seconds after it makes eye contact with the camera. The pulses stop at 9:47:43. That's the exact moment the creature begins its retreat. Audio-visual correlation, Kendrick said. The sound starts while the creature is present and stops when it leaves. That's not coincidence. That's association. But here's the problem. The creature's mouth doesn't open during the pulse sequence, not in any visible way. At 9:47:42, the mouth opens slightly. You can see the jaw movement, but that's 4 seconds into the pulse pattern. The sound was already happening. Whatever is producing it, it's not coming from the oral cavity, not in the way vocalization works in marine mammals. Kendrick walked me through the alternatives. Dolphins produce sound using nasal air sacs. They don't move their mouths to echolocate. Fish that vocalize use swim bladder vibration or skeletal structures that act like drumheads. Some species produce sound through gill movements, rapid muscle contractions that create clicking or grunting noises. She isolated one of the pulses and amplified it. The waveform showed a sharp attack. The sound begins abruptly, followed by a smooth sustain and a clean decay. That's not a click. Clicks are percussive, very short duration. This has sustain. This is a tonal pulse. Something is vibrating in a controlled way. I asked if gills could do that. Theoretically, yes. If the gill arches have musculature capable of rapid oscillation and the surrounding tissue can resonate, you could produce tonal sound. but I've never seen it documented in any species with external gill slits like what's visible in the footage. The anatomy would have to be highly specialized. She ran a harmonic analysis on the pulses. Most biological sounds have overtones, secondary frequencies that occur above the fundamental pitch. Whale songs are rich with harmonics. Dolphin whistles show clear overtone structure. The pulses in the DSSV4 audio have harmonics, but they're faint. The fundamental frequency dominates. That suggests damping, Kendrick said. Whatever's producing the sound is controlling resonance. That's not passive vibration, that's modulated output. Then she showed me the pattern. The 12 pulses aren't identical. 11 of them fall within a tight frequency range, 1.4 to 1.6 kilohertz, but the 7th pulse is different. It's lower, 1.2 kilohertz, and it's slightly longer in duration, 0.4 seconds instead of 0.3. That's variation, she said. That's deliberate frequency modulation within a structured sequence. That's how you encode information. Dolphins do it. Their signature whistles vary in frequency contour to convey individual identity. Whales modulate song phrases across breeding seasons. Even some fish species alter call parameters based on social context. Variation within pattern is a hallmark of communicative intent. I asked her what the pattern might mean. She was quiet. Then, I don't know. 12 pulses is a small sample. You'd need hundreds of recordings to start identifying syntax or referential meaning. But the fact that there's an outlier, one pulse that breaks the dominant frequency, that suggests the sequence isn't just noise. It's structured. It might be communicative. There's another detail. Kendrick ran a directional analysis using phase comparison between the DSSV4's 2 hydrophone channels. Stereo audio allows you to estimate the origin point of a sound based on timing differences between the left and right channels. The submarine's hydrophones are mounted port and starboard, spaced approximately 2 meters apart. The phase analysis indicated the pulses originated from a position roughly 12 meters ahead of the submarine and slightly to starboard. That's exactly where the creature is positioned in the video. Within margin of error, Kendrick said, the sound source matches the creature's location. It's coming from it. Then there's the visual element, the shimmer. Go back to the footage. At 9:47:38, right when the audio pulses begin, the creature's tail exhibits a change in reflectivity. The scales, or whatever the surface structure is, start showing rhythmic brightness variation. Sections of the tail flash brighter, then dim, then brighten again. It's subtle. You miss it if you're focused on the face, but it's there. Dr. Jonas Friedman is a bioluminescence specialist at Monterey Bay Aquarium Research Institute. He's studied light production in everything from dinoflagellates to deep-sea jellyfish. I sent him the video frames showing the tail shimmer and asked if he could explain it. That's not bioluminescence, he said immediately. Bioluminescence is light emission. Organisms produce photons chemically. What you're showing me is light reflection. The creature isn't glowing. It's catching the submarine's LED light and reflecting it back. But the reflectivity is changing. That's active modulation. He explained how it could work. Some cephalopods, squid, cuttlefish, have chromatophore cells that can expand or contract to change skin color and pattern. They also have iridophores, cells with reflective platelets that can be angled to alter how light bounces off the skin. If this creature has a similar system, it could control reflectivity in real time. Open the iridophores, the surface reflects more light. Close them, it darkens. Friedman measured the shimmer intervals frame by frame. The bright phases occur approximately every 0.7 seconds. Each bright phase lasts roughly 0.3 seconds. That matches the audio pulse duration, he said, 0.3 second pulses with 0.4 second gaps. The light pattern is synchronized with the sound pattern. He overlaid the audio waveform with the brightness data extracted from the video frames. The peaks aligned. When the audio pulses, the tail brightens. When the audio stops, the shimmer stops. That's multimodal communication, Friedman said. Sound and light working together. You see it in fireflies, bioluminescent flashes paired with pheromone signals. You see it in some reef fish that use color changes during courtship calls. But I've never seen it in a large vertebrate. And I've definitely never seen it coordinated this precisely. I asked him what function it could serve. In deep-sea environments, visual signals are limited by light availability. Most bioluminescent organisms produce their own light because there's no sunlight. But if you're in the presence of an external light source, like a submarine's LEDs, you can hijack that light, reflect it in patterns, use it to send visual signals without spending metabolic energy on photon production. It's efficient. Which means the creature might have been doing two things simultaneously, producing sound and modulating reflected light to create a combined signal. Audio for long-range communication, sound travels efficiently underwater. Visual for short-range or directional emphasis, light is line of sight, so it's specific. Friedman paused the video on frame 1680, where the tail is mid-shimmer. If that's intentional communication, the question is, who's the audience? The submarine? Something else in the trench? Itself? Kendrick had the same question. Dolphins produce signature whistles to identify themselves to other dolphins. Whales sing to attract mates or establish territory. If this creature is signaling, it's either signaling to the submarine, which implies it recognizes the submarine as something worth communicating with, or it's signaling to others of its species, which implies there are others nearby. The DSSV-4's sonar log for June 14, 2026, shows no additional biological contacts during the encounter window, just the one. But sonar has limits. It's good for detecting large objects or dense schools of fish. A single organism holding still in the water column, especially one without a swim bladder to create a strong acoustic return, could evade detection. There could have been others, Kendrick said, outside sonar range, observing from a distance. If this was a sentinel or a scout, the signal might have been, "I see it, I'm withdrawing, stay clear." Or it was directed at the submarine, a test, an attempt to establish whether the strange metal object with lights was capable of response. Whales investigate unfamiliar objects by vocalizing at them, listening for echoes. Dolphins click train on novel tools to understand structure. If the creature has theory of mind, if it understands that other intelligences exist, it might have been probing for evidence of recognition. The submarine didn't respond. The hydrophones recorded the pulses, but no human on board heard them in real time. The frequency range is audible to human ears, but the ambient noise from the sub's systems would have masked it. It wasn't until months later, when audio engineers isolated and filtered the recording, that the pattern became clear, which means if the creature was asking a question, it received only silence. No echo, no response. Just passive observation from a machine that watched but didn't speak. Kendrick's final analysis ran the 12 pulses through pattern-matching algorithms used in animal communication research. The software compares unknown signals to known bioacoustic databases, whale calls, dolphin whistles, primate vocalizations, even non-vocal communication like elephant infrasound, no matches. The frequency range overlaps with some odontoceque calls, but the pulse structure doesn't fit. The duration and intervals are outside documented parameters for any cataloged marine species. It's novel, Kendrick said, which either means it's a known species doing something we haven't recorded before, or it's an unknown species doing what it normally does. Either way, you've captured something that doesn't exist in our databases. She sent me one last file, a cleaned, amplified version of the 12 pulses isolated from all background noise. I listened to it on loop. 12 rhythmic tones. 11 nearly identical, one different. Then silence. It sounds deliberate. It sounds structured. It sounds like language feels, before you understand the words, patterned, intentional, just beyond comprehension. Friedman ended his report with a single line. If this organism can coordinate acoustic output with bioluminescent modulation in real time, it has neurological architecture capable of complex motor sequencing and sensory integration. That's not survival behavior. That's expression. The footage is 47 seconds. The audio pulses last 5. But in those 5 seconds, synchronized with light reflected off a tail that moves like a mammal's and shimmers like a cephalopod's, something in the deep ocean might have tried to speak. And we didn't know how to answer. The DSSV-4's depth gauge read 1,847 meters when the creature appeared. The pressure at that depth is approximately 185 atmospheres. That's 2,717 pounds per square inch. Enough to crush an unprotected human body instantly, enough to compress air spaces, collapse lungs, force nitrogen into solution in blood and tissue at concentrations that would be fatal during any attempt to ascend. Dr. Marcus Bellamy is a hyperbaric physiologist at Duke University Medical Center. He studies decompression illness, pressure adaptation, and the limits of human deep diving capability. I sent him the footage with one specific question. Could the creature in the video survive at that depth, and if so, what would it cost? He called me 2 days later. The anatomy is the problem, he said. Everything about the visible structure suggests adaptation for depth, except the parts that suggest it can't be adapted for depth. It's contradictory. Start with the gills. They're external, visible slits along the torso that appear to open directly to internal respiratory structures. That's a design that works beautifully at depth because water pressure actually assists gas exchange. The higher the pressure, the more efficiently gills can extract dissolved oxygen. Deep-sea fish with gill systems thrive in the abyss because their entire physiology is built around that pressure equilibrium. But the creature's torso has volume. The ribcage structure visible in the footage suggests an internal cavity, space for organs, possibly lungs, possibly a complex cardiovascular system. If there's airspace inside that body, Bellamy said, the pressure at 1,847 meters would compress it to a fraction of its surface volume, unless the internal pressure is equalized, which requires either constant high-pressure gas exchange or no air spaces at all. Marine mammals solve this problem by exhaling before they dive. Whales collapse their lungs intentionally, shunting blood away from nitrogen-saturated tissue, avoiding the pressure differential that causes barotrauma. They don't breathe at depth. They hold what little air remains and manage oxygen through blood storage and metabolic suppression. But if this creature has functional lungs and gills, Bellamy said, that's a hybrid system. It could theoretically breathe at depth using gills and breathe at the surface using lungs, which means it might be adapted to function across a massive pressure range. That's not impossible. Some marine reptiles managed it, but the metabolic cost is extreme. Then there's the ascent problem. The creature in the footage is at 1,847 meters. For it to have reached that depth, it either lives there permanently or it descended from shallower water. If it lives there permanently, its body is pressure adapted. Its cells, its tissues, its biochemistry, all of it exists in equilibrium with 185 atmospheres. If it tries to ascend to the surface, the pressure drops to 1 atmosphere. The dissolved gases in its tissue would come out of solution. Nitrogen bubbles forming in blood, in joints, in the spinal column, decompression sickness, the bends, fatal within minutes. Unless it ascends slowly, Bellamy said. Humans can dive to extreme depths if they decompress gradually on the way up, but we're talking hours, sometimes days, for the deepest dives. A creature ascending from 1,847 meters would need to stage at multiple depths, allowing gas exchange to equalize at each level. It would need to know how to do that. It would need to have evolved a physiological mechanism that tolerates the transition. Or it doesn't ascend. It stays deep. It lives its entire existence below 2,000 meters, where the pressure is stable and the environment doesn't change. That's the simpler answer. That's what most deep-sea organisms do. But the anatomy suggests otherwise. The eyes are too developed. Deep-sea fish that never see sunlight have either vestigial eyes or highly specialized photoreceptors designed for bioluminescent wavelengths. The creature's eyes in the footage show structural complexity consistent with vision across a broad light spectrum. The tapetum lucidum, the reflective layer visible in frame 1455, is an adaptation for low light, but it's not an obligate deep-sea feature. Cats have it. Nocturnal terrestrial animals have it. It's for hunting at dusk, not for living in total darkness. If those eyes work the way they look like they work, Bellamy said, that's an organism that encounters variable light conditions. That's something that moves between depth zones. Which brings us back to the pressure problem. If the creature can move between depths, it has to manage decompression. And if it was at 1,847 meters when the DSSV-4 encountered it, and if it didn't belong there, if it descended from shallower water to investigate the submarine, then the encounter might have killed it. Bellamy walked me through the timeline. The creature appears at 9:47:29. It remains visible for 29 seconds. Then it retreats and disappears. The footage ends. We don't know what happened next. If it ascended rapidly after leaving the camera frame, Bellamy said, it would have experienced catastrophic decompression, gas embolism, tissue rupture, pulmonary barotrauma. Death would follow within minutes. If it descended deeper to return to its normal habitat, and if that habitat is below 2,000 meters, the pressure increase might have been survivable. But if it stayed at 1,847 meters, and if that's outside its adapted range, the metabolic strain alone could be fatal over hours. There's a third possibility. The creature knew the risk. It understood that approaching the submarine meant entering a pressure zone that was dangerous, and it did it anyway. That's the part that bothers me, Bellamy said. If this organism has the cognitive capacity the behavioral analysis suggests, it might have theory of mind. It might understand risk assessment, and it made a choice to expose itself to potential harm for the sake of observation. I asked what would motivate that. Curiosity, territorial defense, protective behavior. If there were others nearby, it was trying to shield. Or, he stopped. Or it understood that contact was significant enough to justify the cost. The footage shows no signs of distress during the encounter. The gill movements are rhythmic. The motor control is precise. But Bellamy pointed out that hyperbaric stress doesn't always present immediately. You can feel fine at depth and die hours later during ascent. The damage happens on the way up, not on the way down. He froze the video at 9:47:43, right before the creature retreats. Look at the gill flare. That's a sudden increase in respiration rate. That could be preparation for rapid movement, or it could be the first sign of respiratory distress. If the internal CO2 load was building, if the oxygen exchange wasn't keeping pace with metabolic demand, you'd see exactly that, a sharp intake, an attempt to compensate. The creature accelerates out of frame in 1.7 seconds, fast enough to suggest full muscular function, but the trajectory is downward and lateral. It doesn't ascend, it moves deeper into the trench. If it went down, Bellamy said, it might have survived. Pressure would increase gradually, which is less traumatic than rapid ascent. But if it was already outside its safe depth range, going deeper just extends the exposure time. It's buying time, not safety. No follow-up expeditions to the site have been authorized. The DSSV-4 program was terminated 3 days after the footage was captured. No additional dives were conducted in the Clarion-Clipperton zone. If the creature died, its body would have drifted or settled somewhere in the trench. At that depth, decomposition is slow. Scavengers exist, deep-sea amphipods, hagfish, but a body could remain largely intact for weeks. Bellamy's final assessment was cautious. If this creature is adapted to live at depths below 2,000 meters, the encounter was survivable. If it's adapted for shallower zones and descended temporarily, it might have paid for that decision with its life. And if it's capable of moving between pressure zones through some physiological mechanism we don't understand, then everything we know about hyperbaric limits is incomplete. I asked him which option he thought was most likely. He was quiet for a long time. Then, I think something that looks that human, that moves that intelligently, that makes a deliberate choice to approach an unknown object in an environment that could kill it. I think it knew the risks. And I think it came anyway. Which means we might have just watched the bravest thing anyone's ever captured on film, or the last act of something that wanted to be seen before it was too late. Marine behavioral analyst Dr. Keiko Surridge has spent 17 years studying threat displays in intelligent marine species, orcas, leopard seals, Humboldt squid, animals that communicate territorial boundaries through posture, movement, and what she calls spatial negotiation, the way an organism positions itself relative to a perceived threat to signal intent without direct confrontation. I sent her the footage with no briefing, just the 47 seconds. She watched it twice, then stopped at frame 1390. "That's not curiosity," she said. "That's interception. Look at the approach angle." The DSSV-4 returned to port on June 17, 2026, 3 days after the encounter. The mission summary filed with the sponsoring institution, Pacific Marine Sciences Consortium, stated, "Expedition concluded early due to critical equipment malfunction. Primary sampling objectives incomplete. Full technical review required." Dr. Sarah Chen, Dr. Raj Venkatesh, and pilot Marcus Holt submitted individual post-mission reports. All three used identical language regarding the equipment failure, hydraulic system irregularities requiring immediate surface return. Standard protocol language. The kind of phrasing that comes from institutional template documents, not first-hand technical assessment. None of them have spoken publicly since. The footage is 47 seconds. The research program that captured it lasted 3 days longer. The silence has lasted 8 months. Either this is documentation of the most significant cryptozoological discovery in recorded history, evidence of an intelligent aquatic species that has occupied deep ocean trenches for at least 83 years, while institutions that should have been searching dismissed every encounter as equipment noise or misidentified whales, or certain organizations made a calculated decision that the public isn't ready to know we share the ocean with something that watches back. The DSSV-4's camera recorded it. 3 separate sonar contacts across 8 decades described it. Audio analysis captured it, trying to communicate.